Okay, so there's something that we've all seen hundreds of examples of, and we're going to put it on a solid mathematical footing today. We're going to talk about relations. So one concrete example we can think of is we have the less than relation. So we say a pair x and y satisfies this relation if x is less than y. There's a natural way to formulate this in terms of subsets of a Cartesian product. And so today we're going to bring all the stuff we've been doing together into this one idea.
Let A and B be sets. A binary relation between A and B, or sometimes a relation between A and B, is a subset of A times B. If the pair xy is in R, we sometimes write xry. If the pair xy is not in R, we might write xr/y. When A equals B, so that R is a subset of A times A, we say that R is a relation on A. Here we give a series of examples. Let A and B both be the real numbers. Let R be the set of pairs xy with x less than y. This is clearly a subset of R2, and we also call this the less than relation. Example 2, let f be a function from A to B. Let R be the set of pairs x, f of x, where x ranges over A. This is sometimes called the graph of f. Let A be any set, and define R a subset of A times A, where R consists of all pairs AA, where A lies in A. This is sometimes called the equals relation, or also called the diagonal relation. Here, x relates to y if and only if x equals y. Now let A be the set 1, 2, 3, and B be the set consisting of a triangle and a star. Then consider the subset of A times B, defined by the following pairs: 1 triangle, 1 star, 2 star, and 3 triangle. This is a relation from A to B. One last example. Let A be any set, and consider a relation R on the power set of A. Specifically, R is a subset of the power set of A times the power set of A, where we define R to be all pairs B, C, such that B is a subset of C. Now let us define the conjugate of a relation. This is sometimes called the conjugate or the symmetric conjugate. If R is a relation from A to B, then the symmetric conjugate of R is the relation from B to A, defined by R star is all pairs yx such that xy is in R. Basically, take all the pairs in R and flip them. Notice that if R goes from A to B, then R star goes from B to A. We say that R is symmetric if R star equals star. Of course, this only makes sense in the context where A equals B. Let me point out one thing here. This is one place where my notation is very different from the book. Let me explain. We define the symmetric conjugate of a relation R to be the relation R star, where we flip the entries. The book also discusses this notion, but it calls it the inverse of the relation and actually writes R to the -1, like it was a function. In my opinion, this is a very bad convention, and we should not do this. The word inverse should be reserved for the inverse of a function, and referring to the inverse of a relation, I think, is actually more confusing than not. So to be clear, I will not do what the book does and call this the inverse. I will call this the conjugate. So now let us revisit some of our earlier examples. If R is the less than relation, namely pairs xy with x less than y, then R star is the set of pairs yx with x less than y, or we could write this as the set of pairs AB with A greater than B. Therefore, the conjugate of the less than relation is the greater than relation. Okay, now let us assume that f is an invertible function from A to B, key being invertible. Recall the relation x, f of x for all x in A. Then R star is the relation f of x, x for all x in A. But recall, if f is invertible, then f of f inverse of y is y itself. So R star is the set of all y comma f inverse of y with y in the range of f. But again, f is invertible and thus surjective, so that all of b is in the range of f. Therefore, R star is the relation given by the pairs y comma f inverse of y with y in b. To summarize, if f is an invertible function and R is the relation giving its graph, then R star is the graph of the inverse function f inverse. But notice, this only works if the function is invertible, as this was an important feature of what we're doing here. Another example. If we recall the case of R being 1 triangle, 1 star, 2 star, and 3 triangle, then R star is the set of all the pairs triangle 1, star 2, triangle 3. Okay, now for a theorem. If R and S are two relations from A to B, then we have some identities. The conjugate of R is R itself. If R is a subset of S, then R star is a subset of S star. The conjugate of a union is the union of the conjugates. The conjugate of an intersection is the intersection of the conjugates. And when A equals B, we can consider the two relations R union R star and R intersect R star. Both of those relations are symmetric. We won't prove all of these, but let's do one example. Assume that R is a subset of S. Take xy in R star, then yx is in R, therefore yx is in S, and then xy. Okay, now for one last relation. Let's consider the relation on the integers given by divides. Namely, R is all pairs of integers a, b, such that b divides a. It is not hard to see that R star is the set of all pairs a, b, such that a divides b. So let us ask, what is R intersect R star? Specifically, if we know that we have a pair of integers x, y, such that x divides y and y divides x, what can we say? First, note that y equals kx for some integer k, because x divides y. We also have x equals ly for some integer l, because y divides x. Therefore, x equals lkx, which implies that lk equals 1. There are only two possibilities for integers. Either L equals K equals 1, or L equals K equals minus 1. In particular, either Y equals X or Y equals minus X. Therefore, R is the set of all pairs AA plus all pairs A minus A, where A is an integer.